Hello everyone, my name is Richard and in this week we'll be having a two-part series to prepare you for your final exam with a final review. So in this video we'll be covering chapters 18 and 19, and for this review we'll be solving out several problems. So for chapter 18 we had discussed about the macroscopic description of matter. In this first problem it's given here. 2 liters of an ideal nitrogen gas are at 0 degrees Celsius and 1 atmosphere. It's a 3-part question. So determine the number of moles of nitrogen gas, how many molecules of nitrogen gas are present, and what is the mass of this gas? All right, for the first part, let's begin to solve it. We should first write down what we're given. In this case, we know the volume, temperature, and pressure. What we need to find is N, or the number of moles. We also know that there has to be some unit conversions involved because when we solve out a problem, we have to be able to be consistent with standard SI units. And we also need to know the universal gas constant as well. So if you don't know this, it will be given on the exam. So when we do these conversions, we will obtain the following in cubic meters, Kelvin, and in pascals. So this is a pretty simple equation. You're using PV equals nRT, and you have all the information that's been highlighted. So I just did that for you guys. And you just plug those numbers in, and you get 0.089 moles of nitrogen gas. All right, so for part B, how many molecules of nitrogen gas are present? So we need to figure out what we know. So we know that the number of moles which we calculated was 0.089 from part A, but we also need to consider something else. We also need to consider Avogadro's number because that relates the number of molecules to the number of moles, which is given by that value, 6.022 times 10 to the 23rd. So this, to obtain the number of molecules, it's basically multiplying the number of moles to the number of molecules per mole. It's pretty straightforward. You just have to look at the units and figure out which ones cancel each other out. So in the end, you get 5.4 times 10 to the 22 molecules. This is just one way of solving it. There's actually an alternative way. If you guys remember from one of the previous videos that I covered, the alternative equation is to use PV equals to NKBT. So keep in mind that capital N is the number of molecules and lowercase n is the number of moles. So when we solve this out, we also know that Kb is what we call the Boltzmann's constant, and it's the relationship between Avogadro's number and the universal gas constant. So when we solve it out, we still end up getting the same value for the number of molecules using the same pressure, volume, and temperature which we used before. Finally, what is the mass of the gas? What we know is from part A, once again, we have 0.089 moles, but we also need to know the number or the grams per mole of each molecule. So for a single nitrogen molecule, you can figure out from the periodic table that it's 14.007 grams per mole. However, this is a nitrogen gas, and we had specified it was N2, so that means that you have to double it, which is 28.014 grams per mole. And this is just a simple solve to determine the number or the mass of the gas. You're just multiplying the number of moles times this 28.014 grams per mole. What you get is that the mass of the gas is 2.49 grams. All right, moving to chapter 19, which we had discussed about was work, heat, and the first law of thermodynamics. This one is a bit trickier, and that's why we have two problems for this chapter. So let's cover the first problem. A 905-gram meteor impacts the Earth at a speed of 1,623 meters per second. If all of its energy is entirely converted to heat in the meteor, what will be the resulting temperature rise of the meteor, assuming it does not melt? Assume that the meteor is made out of iron. And in this problem, we'll be given the table of specific heats to help you guys figure out some more information. Here we have the table again, and let's figure out what we're given. So from the problem, we basically were given the mass of the meteor and its volume or its velocity once it impacts the Earth, which is 1,623. It said we were looking for a temperature rise. That's another way of saying a change in temperature, or delta T, and that's what we're trying to find. And in the problem, it said all that energy that was converted from kinetic was transferred to heat. So it's basically saying that work is equal to heat for this problem. And in this case, we'll just say that work is, remember, the definition is a change in kinetic energy, and we'll set that equal to heat again. So for the change in kinetic energy, it's 1/2 m Vf squared minus Vi squared, right? Is equal to mass of the meteor times the specific heat, which the meteor was assumed to be made out of iron, times the delta T, or change in temperature. As you can see here, the masses actually cancel each other out from both sides of the equation. So when we simplify it, it's going to be completely removed. Also, another thing is that we assume that the initial velocity is 0, so Vi squared is also equal to 0. So when you simplify it and also isolate for the change in temperature, you get Vf squared Vf squared divided by 2 times the specific heat of iron is equal to the change in temperature. And we know that from the table that the specific heat of iron is 449 joules per kilogram Kelvin. So it's really important to note that there's two columns, and one has kilograms in the denominator while the other has moles in the denominator. But the reason we chose kilograms was because we specified that the mass was in grams or kilograms. We didn't have to convert to the number of moles. So what we had in our third line of the equation, they both canceled each other out because they were in terms of kilograms. So when you plug your final velocity and your specific heat of iron in to the equation, you get a temperature rise of 2,930 degrees Celsius. All right, so this problem says that if you add 700 kilojoules of heat to 700 grams of water at 70 degrees Celsius, how much water is left in the container? All right, so let's figure how to actually solve this problem. We need to figure out what we're given, but we also have to consider the energy temperature graph. So what we're given is that we know that the total energy that we put into the system is 700 kilojoules. We know that the total mass of the water is 700 grams in the container, and we also know that its initial temperature is 70 degrees Celsius. So if we look at the graph below, we can see that I put a blue line at 70 degrees Celsius to show that where it starts, and then there's one above it, which is at 100 degrees Celsius, which is where it begins to be converted into steam or vapor. So as you can see here, I also put a star showing that if you look at the line across from it, there's going to be some water plus some steam, but we don't know the amount of each. So we have to determine what the actual amount of water is left inside the container. So how can we do that? So once again, we have what we're given, and we have to convert it to our standard SI units, which I've done here. And the first step is to determine the heat it takes for the liquid to begin to boil. So it's still in its liquid phase, but once it reaches to the boiling temperature at 100 degrees Celsius, that's when we know that it begins to change into vapor state. So that's where the phase change actually occurs. So how do we do this, right? So we have to use the equation Q is equal to mc delta T again. In this case, your delta T is the change in temperatures. So it's actually 100 degrees Celsius, boiling point, minus the initial 70 degrees Celsius, which is 30 degrees Celsius. And we know from table 19.2, which is given, is that water as a liquid is 4,190 joules per kilogram Kelvin. So we're still keeping it in terms of the first column using the units with kilogram in it and then not moles. So we plug all the numbers in, right? And we get 87,990 joules. So once all that water has been entered that heating stage and it's beginning to change into its vapor state, we have to consider something else, right? So if we continue on with our steps, we have to determine that next is to determine the amount of heat left in the phase change. So we want to determine that amount, which is simply the total, which was inputted into the system, which we originally were given as 700 kilojoules, and we're subtracting the heat from the change, or from its entire heating point from 70 degrees to 100 degrees Celsius, which is highlighted in light blue. So once we do that math, we get that value. And next, we want to calculate the mass of water that has been vaporized. So we're using the equation Q is equal to mass of the vapor times the latent heat of vaporization. You'll be given this value. In this case, I gave it as 2,260 kilojoules per kilogram. So we simply have to determine what the mass of the vapor is, or vaporized water is. So that is just taking that leftover amount of heat from the phase change, and we're dividing it by the latent heat of vaporization. So in this case, once we do that, we calculate it to be about 271 grams of water that has been converted into vapor. But the question is asking, what is the mass of the water remaining in the container, right? So what we calculated here is the mass of the vapor once all that heat has been, transferred over. So in this case, the mass that has been left over is the total mass subtracting the mass of a vapor that had been changed, right? So in this case, it's 700 minus 271 grams is equal to 429 grams, which is the leftover water in the container. So that concludes part 1 of this final review session. I hope that really helped you in understanding some of the ideas of combining everything together, and I look forward to seeing you in the next video soon. Thank you and take care.